Hello, everyone. Thank you for joining the National Stock Assessment Science Seminar Series. My name is Bailey, and I coordinate this monthly seminar series that highlights interesting advances and topics in stock assessment science. Today, we are pleased to have Dr. Steven Saul with us. Steve is a contractor with ECS Federal, working with NOAA Fisheries Office of Science and Technology, and also an assistant professor at Arizona State University. His research applies an interdisciplinary system-based approach to understanding tropical marine resource dynamics, the ways that humans use these resources, and the feedback between humans and the natural system. In today's seminar, Steve will discuss how fisher behavior can bias stock assessment. Without further ado, I'll pass it over to Steve.
Okay, so as Bai mentioned, I'll talk a bit about some of the research I've done looking at fishing behavior and how it can impact stock assessment. And I'll share with you a case study from the Gulf of Mexico. And so first, just as a bit of background, human behavior and uncertainty are really important components to the variability that's contained in fishery stock assessments and important components in variability with respect to developing policy solutions based on fisheries assessment outcomes. And so to explore this a bit more, I've been interested in where or where in the sort of stock assessment modeling process biases due to human behavior may come into place and could potentially cause challenges or cause the outcomes or the results of stock assessments to be a bit different from what system dynamics really might be in the ocean. And so to do that, I developed an agent-based simulation model of the Gulf of Mexico. I'll talk a little bit about the simulation model and how it's developed, but I'll point you all to some references in case you want more of the technical details. But I'll just sort of go through kind of quickly how the simulation model is structured, and the simulation model essentially develops fishery-dependent data, which is then put into stock synthesis 3, and for the species that are in the model, and an assessment is run, and then the outcome or the results of the assessment are compared with the status of the fish populations in the simulation model to see how closely or not closely the assessment can match the state of each resource. And then I'll talk a little bit about some additional applications of models to understand fisher behavior and for fisheries management, and where this research is headed, essentially future research. So just again, a bit of background. Fisher behavior is a key source of uncertainty in both fisheries assessments and in fishery policy development. You can see Beth Fulton's paper from 2011 provides a really good review, as do several other manuscripts that have come out. A lot of the attention's been focused on modeling, getting the sort of biological data uncertainty right, and model uncertainty, and that's of course important. But there's also this other component of uncertainty related to human behavior that has received less attention. But it's important because for those of us in regions that rely on fishery-dependent data to drive indices of abundance in our stock assessments, and even just looking at and incorporating catch and landings, any data from the fishing industry, commercial, recreational, etc., is going to essentially be impacted by the decisions that the fishers made when they went out fishing. Fishers are not scientifically sampling, of course, and so the data is a product of essentially where they fished, what they targeted, how they fished, etc. So to explore this question a bit, I developed an agent-based model. I'm not going to really sell folks on agent-based modeling in this presentation for the sake of time, but the idea is to essentially reproduce fish population dynamics and the behavioral dynamics of the fishing fleet, allow these entities to interact across space and time under realistic state conditions, and then write out the data that explains the status of the natural state in the simulation, as well as the data from the simulated fisheries, put that data into stock assessment and see what happens. Agent-based modeling is a really useful tool to study coupled human natural systems and the feedbacks between them. There are quite a few fisheries agent-based models out there now. And again, it's a really great way to look at the couplings between the human and the natural system, and sort of understand how these affect one another and feed back on one another. So the simulation model of the Gulf of Mexico, there are a couple of versions out there or that have been developed so far. The initial version, or legacy sort of version, just covered the West Florida shelf and was programmed for the time period pre-IFQ. That was work I was doing as a PhD student and a little bit thereafter. And then there's a second version of this model that was developed thanks to funding from the Gulf of Mexico Research Initiative from GOMRI, which covers the entire Gulf of Mexico and essentially incorporates the individual fishing quota system in it, and as well as the sort of more of an updated regulatory landscape. The work today with respect specific, so I'm going to talk about the model, kind of both versions, when I describe how the simulation model is set up in a few moments. But do know that the assessment part of the work came from the sort of legacy version that just covered the West Florida shelf. And for folks that are familiar with these fisheries, it's really tempting to when we look at trends over time, and in a little while, it's really tempting to think, oh, well, that doesn't follow the trend I know, from stock assessments or what's actually happening in the fishery. But do keep in mind that although, as I'll demonstrate in the next several slides, there's a lot of realism built into this simulation model. At the end of the day, it is a simulation model. And the purpose of this tool was not to develop something that exactly matched reality, although I'll show you when we look at model validation that a lot of the components that were important, a lot of the sort of realistic components that were important were captured. But the main goal is to develop a tool that represents some of the important processes that drive fish and fisher dynamics. So the model represents the first version, both versions of the model explicitly model the longline and the handline fishing fleets that fish for the reef fish complex in the Gulf of Mexico. The legacy version of the model contained the 4 species that you see here. Their pictures depicted here: red grouper, gag grouper, mutton snapper, red snapper. And then the full model also adds gray triggerfish, tilefish, vermilion snapper, and yellow edge grouper. And in both versions of the model, both the fish and the fishing boats are what I'll call agentized, where each entity either represents an individual fish or an individual fishing boat. So you have millions and millions of these things moving around across simulation, time, and space, and interacting with one another. There are several sort of layers to the model. There's a structural layer where things like bathymetric data are stored. Space is divided up into different grids and sectors. You have things like state conditions, a calendar, things like wind speed and fuel price that are important to decision making. Those are all contained in the sort of structural layer. And then you have an ecological layer that has the different species and their life history parameters, simulates their abundance, their growth, maturity, spawning, migration, and their mortality, either natural or yeah, and their natural mortality. And then lastly, there's a human layer, which contains the fishing vessels, all of which are initialized with realistic characteristics in terms of vessel length and engine size and fishing power metrics, those kind of things. There's a cognitive model which helps vessels just decide when they're going to go fishing, where to fish, and then how long to stay out fishing. The second version of the model explicitly represents the individual transferable quota system, and has ex-vessel prices and the ITQ market working in it as well. Just a bit about the sort of spatial structure. So at the finest sort of resolution, there are these grid cells, as you see on the screen, which are about at 1 minute by 1 minute latitude and longitude, which equate to about 1.8 square kilometers in this region of the world. From those, within each grid cell are where the fishing boats and the fish sort of exist and interact. Then there are these larger sort of polygons, which are represented by the intersection of these bands of integer latitude or longitude, depending on what part of the Gulf of Mexico you're in, and these other uh, vertical squiggly lines, which represent 20-meter depth contours. So, for example, this would be one polygon. Next to it here would be another. And so these polygons were used, I'll talk about in a minute, but used for decision making in terms of where to go fishing broadly, and then more specifically, then a fishing boat was placed in a grid cell within that polygon. So first, we figured out how to spatially distribute fish. The legacy version of the model uses estimates of variograms together with simulating the spatial autocorrelation patterns that those variograms picked up to develop plausible sort of uh, uh, distributions of fish populations across space. Within each of these sort of polygons that I was pointing out a moment ago, the overall abundance in each of these polygons is divided up based on an estimate of spatial catch per unit of effort. So you take the total estimated abundance from the most recent stock assessment and divide that up and place each of those abundance amounts in each of these polygon regions. And then you can further simulate that out within that each polygon using the spatial correlation found between these animals. So that's sort of how animals are distributed across space in the legacy version. In the full golf version, the newer version, we used an ensemble of machine learning models, which together with habitat data to model or represent the spatial distribution of fish across the Gulf. I, again, won't go into details. The references for each of those manuscripts are here, and if I'm happy to talk about technical details at a later time offline. Here, so that was just an example of distribution for red grouper. Here's an example for red snapper, just to give folks a sense of what these machine learning models produced. So then for the ecological layer, we borrow the abundance at age, the population demographics, so survival and recruitment functions, estimates of national mortality, and other life history parameters, growth, maturity, etc., from the most recent stock assessments for each of these species. In both versions of the model, recreational fishing mortality is not modeled explicitly as individual fishing agents. It's just modeled as one overall fishing mortality that's uniformly applied across space and time. That's something that's currently sort of planning to improve in the model and get to a point where that can be modeled explicitly. The time step of the simulation is daily, so each time step is one 24-hour period, and recruitment occurs at the start of each year and just follows the spawning recruit function estimated from each stock assessment. Spawning biomass is the sum of mature individuals across space and time that's just added up at the end of each simulation year. And then newly recruited age 0 fish are placed in what I define as nursery habitat, which is area that's close to the shore with between 0 and 20 meters of depth. When fish in their nursery habitat reach maturity, they will ontogenetically migrate offshore to sort of predestined habitat locations based on the species distribution maps that I just sort of showed. And we felt it was important to capture this sort of a migratory process because a large amount of the fishing mortality that occurs sort of picks off or removes these animals as they're moving offshore once they're kind of recruited to the fishery early on. The legacy version of the model used a bias random walk with different rankings to model the movement of these fish from inshore nursery habitat to offshore habitat. Again, details can be found here in this reference. We've made quite a bit of improvements on this by still using a bias random walk algorithm, but instead we're using the turning angle approach, where turning angles and distances are drawn from a beta distribution. And this allows a lot more flexibility in the sort of migratory paths that fish can take, and makes them a little bit less rigid or locked to the sort of ranked approach that was implemented before. And it allows fish to a lot more easily migrate, since given the geometry of the Gulf of Mexico, with these sort of curved coastlines, it allows fish to sort of better handle the curved coastline and move or migrate along a parametrically defined curve when necessary. We had algorithms in there to get fish out of bays and estuaries, but that was greatly improved upon and made a lot more computationally efficient. So then the human layer is informed by a handful of discrete choice models, which are estimated from the logbook data by combining the logbook data with converting it to panel data set and to a panel data set, and combining that logbook data with other state condition observations, so things like wind speed and vessel characteristics, prices of fish and fuel, uh, policies and such. And then we initially surveyed a handful of vessel captains to determine what the most important sort of variables are when they're making these decisions. And then those were the variables that we collated data on and sort of merged into this panel data set and used to fit 3 discrete choice models. One, a binomial logistic model for the participation decision, so when someone goes to take a fishing trip; a multinomial logistic model for site choice, so where does someone go and fish in any of those across any of those polygons; and then once a vessel's out fishing, how it decides to return to port. So what are the different factors that help make those decisions? Once we statistically fit these 3 models, the fitted parameters were incorporated into the simulation model, and the fishing vessels used those parameters and multiplied them times the state conditions at the time. So, for example, the wind speed parameter would be multiplied times the wind speed that day in the simulation. You add up the product of all those variables and associated state conditions, and you end up with your probability of making that decision. Draw a random number, and then that's how vessels decided whether or not they would make that choice. Some of the patterns that came out of that modeling that you can see, these are partial probabilities on the y-axis you see. So it makes intuitive sense that as wind speed increases, your partial probability of going out fishing would decrease, or at least the probability that's contributed with respect to wind. So as wind speed goes up, you're less likely to want to go out and take a trip. Things like policies, when fisheries are opened or closed, obviously impacts whether or not a fisher will go out and take a trip. fishing location, fuel price determines how far out you're going to go. When fuel prices are higher, boats are less likely to travel as far offshore as they would otherwise. And then, of course, returning to port, things like as you start filling up your fish hold and run out of space, that's going to also essentially uh, motivate you to return to port. So there were other factors in these models. These are just a couple plotted examples so you can see how some of the trends came out. In the full Gulf model, we parsed time into these three blocks. So this pre-time period, which was before Deepwater Horizon and before the individual transferable quota system was put in place for most of the reef fish species. Then there's this sort of Deepwater Horizon / IFQ period, and then this sort of pure IFQ period. This analysis needs a bit more work before it can be published. It's sort of still in its prep phase in order to more realistically kind of get out of these sort of discrete models, the choice models, the impact of Deepwater Horizon versus the IFQ system, since both happened around the same time in the same year anyway. And then lastly, on the human layer side, the individual transferable quota model was borrowed from work that Rich Little et al. Did in 2009, where they baked a ITQ model into an agent-based model as well. So we implemented their approach in this model, and that's again in the second version of the full Gulf model. For the fishing vessels, there's some limited amount of learning that can happen. So the vessel agents keep a record of their own in other words, each simulated fishing boat keeps its own personal logbook and record of its own personal CPUE, which it helps use to make site choice decisions. Although the behavior can be somewhat said to be fixed based on the use of the discrete choice parameters, the decision each day can vary quite a bit as state conditions vary, and as the year progresses and a vessel's sort of profit is increasing or not. That can also help influence their decision making. There's quite a bit of variability in assigned vessel fishing power, vessel characteristics, all of which were calculated from actual data and then put in the model so that the simulated fleet best represents the fleet in reality. Catchability and retention functions are used, and then the observer data is used to understand on one given day how many times a vessel will move from one spot to another sort of locally. So once a fishing vessel selects sort of a large sort of polygon in which to fish, it can then move within that polygon a variety of times that day, which is drawn from a probability distribution from the observer data. And then the distance and direction it moves is also drawn from probability distributions coming out of observer data. So when you put all of these components together in the simulation model and you run it for 20 years and collect simulated logbook data, we'll talk about now what came out of that, essentially what we found. And so one of the things we wanted to look at very closely was catch per unit of effort. And so human behavior is a sort of, if you're using fishery-dependent data sets to calculate catch per unit of effort, which is done in fisheries where we don't have very good surveys or for species that are not well surveyed, then human behavior and human bias is sort of wrapped up in that data. And so one of the things we wanted to see was whether or not CPUE standardization could sort of standardize away or remove that source of variation from human behavior and get us closer to an index that looks more similar to trends in abundance and would perform better in a stock assessment. So to look at that, in the Southeast, we don't have a lot of factors readily at our disposal. So a lot of our standardization models don't always contain a lot of factors. I think that's changed since I was working as an FTE with the agency. But oftentimes there were just a few factors like year, area, month, and sort of number of days away fishing that could be used to standardize CPUE. What I did was, so I used sort of that small sort of subset of variables to generate one standardized index, and then I used a whole bunch of other variables for which I had information from the simulation model to develop another set of indices that could be used. And these are all the variables, so year, area, month, number of locations fished, and travel time, fish prices, the vessel characteristics like speed and length, allocations and fish hole and such, just to see if including these other variables that are linked to sort of the human dimension or domain and human decision making, if that's a way to sort of remove that source of uncertainty. Well, it turns out that so here these figures show the amount of deviance from the standardization models, from the generalized linear models that were fit. The purple bars represent the sort of typical assessment that I showed you, that very small table with just 4 factors in it, and then the blue bars represent the sort of extended uh, CPUE standardization with the larger list of variables. And what you'd see is that for the we use the sort of typical delta log normal approach. And what you'd see is that for the binomial models, it didn't really matter that much, that the amount of deviance or the fraction of uncertainty sort of accounted for didn't really change much, regardless of whether or not you loaded those models up with all those additional factors or not. But for the log normal portion of the models, a lot more deviance was explained, in generally speaking, for 3 of the 4 species when you added those additional factors. However, despite explaining a bit more of the variability, the actual trends in the indices didn't change very much, and still, for some species, did not conform well to the actual patterns in abundance that went on in the simulation. So here, the black lines represent the actual patterns from the simulation model directly. That's just normalized to 1 to fit on the same figure. And then the solid lines are the typical standardization, so using those 4 factors, and then the dashed lines are the extended standardizations using that longer list. And you don't really get a better trend or fit out by adding a whole bunch more variables into your standardization. So then what we did was we said, okay, well, what would happen if we ran a stock assessment? We developed several stock assessment models for each of these species with these different indices of abundance. And how close can we get to the truth? Since it's a simulation model, right? We can play God. We know that exactly what the status of these fish populations are and such. And so what configuration of these models will we need to get as close as possible to so that the essentially the status of the stock that's estimated by the stock assessment model matches the status of the stock that we see at the end of the 20-year time series from the simulation. Life history parameters were assumed to be known from empirical studies and were fixed to those that were used in the simulation model, with the exception of the spawn and recruit relationship, which was fit. So once you run the simulation, we noticed a couple things. One, that the model, the stock assessment model, when you run the stock assessment model, I should say, with the simulated fisheries data, a couple things were off. One was that, so here points represent available biomass at size from the actual simulation. So by available biomass, I mean this is the biomass at length that's adjusted based on selectivity functions. And then when you compare that with the available biomass that the stock assessment estimated, which are these solid lines or the dashed line, the two don't match very well. So the stock assessment model had a very hard time replicating the distribution at size of the fish available to being caught, essentially. Then when you look at stock status here, so these are 4 Kobe plots for the 4 species. On the x-axis is the current estimate of biomass over its proxy. And on the y-axis is F current over its proxy, so the F ratio. The points, the diamond point that you see, gray diamond, represents where the status of the stock actually in the terminal year of the simulation, so year 20 of the simulation. And then the other points are from the stock assessment runs. And so open circles here represent what I'm calling perfect information, which is where I put the actual trend coming out of the simulation model into the of catch-per into the into stock synthesis as catch per unit of effort, to see if you could get closer to what the actual status of the stock in the simulation. And then these other points are different versions with either the typical standardization, which is the black circle here, extended standardization, again, using the indices that had more factors in them, which is the gray circle. And then the triangle is what I call perfect length. So I put both perfect information, and I put essentially the length distribution of the population into the stock synthesis model, instead of the actual catch-it length, to see if that would bring us closer to reality. And what you would see is that in general, for most of these species, the stock assessment estimated management, essentially the status of the stock, different from what it actually was coming out of the simulation model. And I'll talk in a minute now about some of the reasons for that. So when you look at sort of partial log likelihoods coming out of these stock assessment models for these various scenarios, you would see that the perfect information and length sort of scenario doesn't necessarily always get you sort of the lowest percentage of log, or sorry, I should say, helps explain a lot of the log likelihood. Less of that is sort of that error is sort of explained with other indices. And then the length distribution really mattered. So the model had a hard time, especially with red grouper and gag grouper, sort of recreating or capturing the demographics of the population structure. So why was that, right? How come when we looked at Kobe plots, things did not line up well to what happened in the simulation? And why do CPUE trends not line up very well? And why are we having issues with the length composition data? The main reason is essentially, if we animate this, you'll see on your left-hand side, fishing effort across space, and then on the right-hand side, how biomass is changing over time. And I can run that through again so folks can see. But what you would notice is that a lot of fishing effort is concentrated in roughly the same places over time. And so it's the old problem of, essentially oversampling in some places and undersampling or not sampling at all in other places. And so ending up with local issues of localized depletion, and all of the sort of issues that brings with catch per unit of effort indices and such. Um, and so we all kind of have this romanticized idea sometimes in our mind that fishers are out exploring the ocean and looking for, great, exploring new places to fish. But in reality, and when you talk to fishers in the Gulf, they're not doing much exploring at all. They have their sort of logbook of places where they know they can get fish. They get an order from a broker or a restaurant for X number of pounds of fish. They know that they need to produce that in 2 or 3 days, and they go to the places where they know they can get those fish. And so that's why you're seeing sort of repeated observations coming from the same place year after year, and thus the assessment, and thus sort of a bias in your indices. So we know a lot about what's going on with the population here and very little about what's going on in the population in other places. We validated some of the fish and catch patterns that we saw across space to VMS patterns, and found that the simulation was able to produce very similar sort of catch patterns in general. This is comparing for red grouper, and this is a comparison for gag grouper, which is not quite as similar, but still some similarities in spatial distributions. So in summary, for this sort of simulation exercise, local depletion was sort of the major problem causing biased spatial sampling. So essentially biased fishing, and that where fishers were not fishing across the entire range of the stock. And so you saw changes in population demographics in some areas where high depletion was occurring, and a very different set of population demographics in other parts of the the stock area where less depletion was occurring. Spatial effort and fishing activity is affected by things like weather and fuel price and fish price, policies and such. So that's important to keep in mind, that if we need to use fisheries-dependent data in any capacity, even just as input from catches or landings, we need to be aware that folks are, not going to be able to fish when conditions are not suitable, right? And so as a result, you're not going to obtain observations during those times. If during closed seasons, you're not going to obtain fishery-dependent observations, etc. Trip duration, it was observed both in the empirical data and in the simulation that trip duration was sometimes limited by hold size, and this really suggests that there's probably effort saturation effect also occurring with CPUE indices. So if fishers are ending their trip just because their boat, they filled their hold capacity, then it's not really reflective of CPUE, because they could keep, essentially fishing in theory, if their hold size was infinite, and continue sampling. So incorporating extra variables into CPUE standardization does not guarantee an improved index. It could help explain some of the variability, but not as much as I was hoping or I thought from that exercise. And then these same challenges could impact fishery-independent surveys, depending on how they're designed and if changes are forced to happen to some of these surveys. So, for example, if with the sort of new push toward offshore wind, as areas become unavailable to survey from our fishery independent efforts, we very close look at how the sort of pre and post installation of wind turbines affects these indices is going to be really important work, so that we can develop or use unbiased indices from these surveys in our assessments. So recommendations going forward are, it's really important to reweight your input data streams when necessary. That goes for logbook catch and effort data. Ensure landings are representative of the stock that's being assessed. And of course, composition data should be weighted according to the landing, so that it's a reflection or a representative of the catch. Surveys could be used strategically to gather information and locate. So for fisheries that are heavily reliant on fishery-dependent data, surveys could increasing fishery-independent survey effort in areas where we're not getting a lot of fishery-dependent data could help to fill some of those gaps. And then just highlighting the importance of sensitivity testing in our stock assessments and applying sort of assessment model ensemble approaches to ensure that we capture these possible uncertainties in data inputs across sort of a range of scenarios. future work for the Gulf of Mexico tool. So my next sort of move with this work is to develop the tool into a projection software. So that can be used to test a variety of different policies. So essentially developing a policy simulator tool that could be used together with conventional projections, but would also provide more realistic projections and would help us and help managers, help councils, the Gulf Council and the Gulf SSC, um, make best informed policy decisions by actually simulating out some of these policies and their potential effects on the natural system and as well as on the human system, and how fishers will behaviorally respond to these policies. To do that, the model has to be restructured, and fish need to be de-agentized, and also the next sort of development, another move for this model is to explicitly model the recreational fishery as agents. Also find ways to future research sort of unrelated to this is to look for ways to combine or embed discrete choice modeling into stock assessments. But that's very challenging just because it adds a lot more parameter to the optimization sort of landscape. And it's hard enough to optimize and fit some of these discrete choice models, especially those that you're fitting for space, because if you break up space into small areas, it can be pretty. You would need a lot of computing power to sort of and computing time to get those models to converge and fit. Agent-based models could also serve as a really useful stock assessment infrastructure as sorts, but maybe with a wrapper that's used and an optimization algorithm that's used to fit to empirical data. So that's sort of another direction of research, but further down the line. I'd like to further explore sort of biases in length sampling as well, and then implications of climate change on sort of the coupled human natural system in the Gulf of Mexico and elsewhere. Um, Aside from the Gulf agent-based model, I've also helped develop another fishery agent-based model called Poseidon, which is more of a policy simulator. It's sort of simple on the biological side, but has more complexity on the human side. We developed an application of it for the U.S. West Coast groundfish fishery, where this is just eye candy of boats going out and from port and fishing for some of the groundfish species to give you all a sense of how the model was structured. And from that, we looked at different sort of agent fisher decision making, kind of machine learning algorithms for fisher decision making, and saw that some outperformed others in different ways. In general, adaptive agents did much better than agents that followed sort of statistical approaches. So agents that followed strict discrete choice models that were fit to the West Coast groundfish logbook data performed worse or less realistically, let's say, than agents that had some freedom or autonomy to adopt. We also, for Indonesia, developed some agent-based models to look at the potential policy trade-offs. And here, what this is showing is sort of there were discrepancies between large boats fishing for reef fish and small boats, where small boats were missing out on a lot of the profit because large boats were catching the majority of the catch. And so the government was asking us to explore policies of, what if can we reduce the maximum number of fishing days for large boats, and what impact would that have on small boats? And if you develop a simulation of this and run this over a whole bunch of different scenarios of maximum days out, you'd find that limiting the maximum days out to 100 or fewer helps small boats start make a profit within 5 to 6 years um, from when the terminal year was for this fishery. And then lastly, the Poseidon model has been applied to the tuna fishery in the Eastern Pacific Ocean as a tool to try and understand if limiting the number of fish aggregation devices that are deployed could be used as a management technique to sort of manage the number of or reduce, sort of limit catch in some way, and effort by limiting or managing the number of fads that are out fishing. So a lot of this work was the Gulf of Mexico work was a lot of the effort was, and a lot of help I had and information was provided to me by the industry. So a huge thanks to a lot of the commercial fishing industry folks along the Gulf Coast, and commercial fishing associations. Special thanks to these four folks who spent a lot of time with me when I was a PhD student, teaching me about fishing in the Gulf, and teaching me what they do and how they do it. And I've become a much better fishery scientist as a result. And we drank a lot of beer together too. That was good. And then lastly, funding. The work has been funded from the Southeast Fishery Science Center through their consortium, through their relationship with the University of Miami, through the joint CMUS Institute. Also was funded by NOAA and Sea Grant, and from GOMRI, the Gulf of Mexico Research Initiative, as well, and University of Miami. So yeah, thank you all for joining, and I'm happy to take questions from folks.
Excellent. Thank you so much. This is Lisa, your host from NOAA Library again. Um, we have about, let's see, we have about 10 minutes to answer questions. So if you have a question in the audience, we'd love to hear them. Just go ahead and type them in the Q&A chat, which is unique from our audience chat, and I will upload them for Steve. And if you know someone who might want to catch the recording of this presentation later on, it will be available on the NOAA Library YouTube channel later today, probably in about 2 or 3 hours. And I'm going to send that link right now so that you can share it. We did get some questions in our chat while you were talking. Early on, we had somebody named Mitchell asked, are you going to add in prey fish abundance per area?
Yeah, that's a good question. It's something I would like to do. It's but probably in the context of coupling it to an ecopath model. So where the two models communicate with one another. So you would run one model, and the output from that one model would inform my model, and then the output from my model would inform ultimately eco space. You would want to get to the eco space phase. So it's not like high on my list to bake in explicitly, but it's certainly something I've thought a lot about, and would be interesting to model one day. I don't know, one step at a time, I suppose.
We also got a second question from the same person asking, is catchability a random function or derived from preferred habitats and their physical properties?
Sure, yeah. So the catchability functions that were used in the simulation model were those that were fit for those species and for those fleets from the most recent stock assessments from those species. And then catchability estimated in the stock assessment models that assess the simulation data, those were fit. Actually, the parameters were fit during the model fitting process for those stock assessment models.
Great. I'm not seeing any other questions. I'm going to give the audience a minute. Meanwhile, if you had any last comments, please feel free to have them.
No,
Right.
nothing else for me.
Excellent. Well, let me thank you so much. I really appreciate you sharing your work with us today, Steve. And audience, I would like to encourage you to join us in a month on October 3rd, the first Thursday of the month at 3 p.m. Eastern Standard Time for the next Stock Assessment Science Seminar. Bye. Thank you for organizing this wonderful series for us. And everybody have a great day, and we'll see you again soon. Take care. Bye-bye.